2026 AIME 1 problem number 4. Find the number of integers less than or equal to 100 that are equal to a plus b plus ab for some choice of distinct positive integers a and b. So first we know that the number a plus b plus ab is going to be less than or equal to 100. That's one condition we have. And just looking at this, or I think it's going to be easier if we rewrite it as ab plus a plus b, this looks like Simon's favorite factoring trick, which is basically a plus 1, b plus 1. And this simplifies to ab plus a plus b plus 1. And just by pattern recognition, we see that these two things are the same. So let's try to make it into this form. So we get a plus 1, b plus 1. And since we're adding 1 to the left-hand side, we also have to add 1 to the right-hand side, are going to be less than 101. So you want to find the number of integers less than or equal to, I guess in this case, 101 for some choice of distinct positive integers a and b. So instead of counting the number of integers that are less than or equal to, or that can be represented this way, let's count the number of integers that cannot be represented this way. So let's use something called complementary counting, which is counting the number of things we don't want, then subtracting by the total number of things. So let's see what we can't have. We know that a and b are positive integers, or natural numbers, which is like 1, 2, 3, and so on. So none of these terms could ever be 1. And therefore, if this can be 1 or this can't be 1, we can't have any prime numbers at all. So that's the first thing we can't have. The first thing we can, or not a text box, the first thing we can't have is no prime numbers. So let's just count the number of prime numbers that are less than or equal to, I guess in this case, 101. A quick way you could do this is if you have the fact memorized that there's exactly 25 primes less than 100, that's going to be useful. And if there's 25 primes less than 100, 101 is also prime, so plus 1. So there's 26 prime numbers that cannot be represented using this sort of representation here. And I guess one key thing that we should have noted is instead of keeping it as this inequality here, we know that our number, let's just call our number n, is going to be equal to a plus 1, b plus 1, minus 1. And so we're basically finding the number of these n that cannot be represented by this. So it's not technically the prime numbers themselves that we can't represent, but the numbers that are 1 less than prime numbers. And so since 101 is prime and 100 is 1 less than that, 100 cannot be represented using this sort of representation that's given in the problem. But if you don't have the fact that there's exactly 25 prime numbers less than 100, you could also just list them out starting like 2, 3, 5, 7, and it does not take that long. It took me like 30 seconds on the actual test because I did not have this memorized. So first we have that there's no prime numbers. But we also have this other fact that we haven't used. We've used the fact that they're positive integers, and so we've derived that there's no prime numbers, but we haven't used the fact that they have to be distinct. And so if a is not equal to b, let's count the numbers that are represented where a does equal b. If a does equal b, then we get a plus 1 equals b plus 1, so our representation is 1 less than a perfect square. So there's no perfect squares. But there's a catch to this statement because it's not that every single perfect square can be represented. So like for example, let's take a look at 4 squared is 16. And so if we wanted to represent the number 15, we need a and b, so that gives us 16. But we know that a plus 1 and b plus 1, we know this case is not going to work. But we also have another case. We can say a plus 1 is going to be 2, and then b plus 1 is 8. This does work. So even though this is a perfect square, we can use this other factorization of the perfect square to get a valid solution. And so it's not all perfect squares. There's sort of a catch here, the catch being that it's perfect squares of primes. And since 4 is not prime, we can actually decompose this further and find a factorization that does work. But for example, if we're at 3 squared equals 9 and we want to represent 8, the only way we could ever possibly get 9 is either 1 times 9, and since we can't get 1, it's at 3 times 3, and since both of them can't be 3, we just can't get 9, and therefore the number 8 cannot be represented. So let's just find the number of perfect squares of primes that are less than 100. So we know 2 squared works since that's 4, 3 squared works since that's 9, 4 is not prime, so 5 is prime, 5 squared works, that's 25, 6 is not prime, 7 squared works, that's 49. 8 is not prime, 9 is not prime, and 10 is not prime. And once we're past 10, we're going to be past our limit, since 11 is the next prime, which is 121, which is past our limit. So we now have an extra 4 numbers that cannot be represented. So we have a total of 26 numbers from the first condition plus 4 numbers from the second condition equals 30 numbers that cannot be represented. And so just doing the final step, 100, which is the total number of numbers, minus 30 numbers that cannot be represented, is 70. So 70 numbers can be written that way. And since it's AIME, we have to write it 0, 70.